Look up at the night sky, and you might assume you're seeing millions of identical, glowing dots. But the universe is actually populated by a bizarre zoo of stellar objects, and every detail of a star's existence, from its temperature to how it will eventually die, is dictated entirely by a single number, its mass. At the absolute bottom of this mass scale, we find brown dwarfs. These are massive balls of gas, weighing between 13 and 80 times the mass of Jupiter. They formed exactly like stars, but failed to accumulate enough mass to ignite ordinary hydrogen fusion in their cores. If you add just a little more mass, you cross the threshold into true stars. Red dwarfs are the smallest, coolest, and dimmest true stars in existence, yet they dominate the galaxy, making up roughly 75% of the entire stellar population. Plotting star mass against lifespan reveals an extreme inverse relationship. The heavier the star, the faster it dies. Small red dwarfs sip their fuel, burning for over 1 trillion years. But the universe is only 13.8 billion years old, meaning no red dwarf has ever died. Astrophysicists predict that when they finally run out of fuel, they will heat up and turn into blue dwarfs, but for now, these objects remain completely theoretical. In a violent universe full of massive, explosive forces, the smallest and dimmest objects win the ultimate survival game simply by starving themselves of fuel. Moving slightly up the mass scale, we find orange dwarfs and yellow dwarfs. Our own sun is a yellow dwarf. These stars burn hotter and brighter than red dwarfs, and their lifespans can be measured in the tens of billions of years rather than trillions. Orange dwarfs sit right in the middle, and astronomers consider them the absolute best candidates for hosting habitable alien planets. They offer an incredibly stable environment, producing fewer dangerous solar flares than red dwarfs, while still giving life up to 30 billion years to evolve. You might occasionally find much older, dimmer objects called subdwarfs. These are ancient, metal-poor stars found floating in the galactic halo, formed very early in the universe's history before heavy elements were widely available. Far beyond these stable, mid-sized stars are the blue giants. These are massive, incredibly hot stars that burn at surface temperatures exceeding 10,000 Kelvin and shine tens of thousands of times brighter than our sun. But that immense size is a fatal flaw. To support their own crushing weight, blue giants race through their hydrogen fuel at a furious pace, exhausting their supply in just a few million years. Every living star is trapped in a permanent tug-of-war between the crushing inward force of gravity and the outward push of nuclear fusion. And the moment that core fuel runs out, gravity takes over, and the real chaos begins. When a star exhausts the hydrogen in its core, its internal engine stutters. The core violently contracts under its own gravity, and this sudden inward collapse generates so much heat that it forces the star's outer layers to dramatically expand outward. In roughly 5 billion years, our sun will experience this mechanical failure. It will swell into a massive red giant, expanding far enough into the solar system to engulf the orbits of Mercury and Venus. For the heaviest stars in the universe, this expansion creates blue and red supergiants. These are the gargantuan forms massive stars take when their core fuel runs dry and their outer layers balloon into space. One famous example is Betelgeuse, a massive red supergiant burning in the constellation Orion. To understand its incomprehensible scale, if placed at the center of our solar system, its surface would extend past the orbit of Mars, potentially reaching Jupiter. While these supergiant stars dominate the sky in sheer physical volume, their monstrous expansion is a red flag. It tells us they are rapidly losing their battle against gravity and are nearing total collapse. The absolute largest of these are the hypergiants, like UY Scuti. These stars are so immense and so highly unstable that they bleed off their own mass at enormous rates through powerful stellar winds. This instability culminates in the terminal Wolf-Rayet phase. These are massive, dying stars literally boiling off their outer layers, violently ejecting shockwaves of material into space at 2,000 kilometers per second. This violent shedding process completely strips the star, exposing a naked, actively burning helium core that can reach a blistering 200,000 Kelvin. Eventually, these gargantuan, unstable structures can no longer support their own immense weight. The core collapses in a fraction of a second, resulting in a cataclysmic supernova explosion. After a supernova, the surviving core transforms into a super-dense physics anomaly, with its final state dictated entirely by how much mass survived the explosion. For an average star like our Sun, the remnant is a white dwarf. It's a dead, glowing core roughly the size of Earth, but containing the mass of an entire sun, doomed to simply radiate its remaining heat into space and slowly cool over billions of years. But massive supernovae leave behind something far more extreme, a neutron star. This occurs when an entire sun's worth of mass is violently crushed by gravity into a sphere only about 20 kilometers wide. The density here completely breaks human comprehension. The neutrons are compressed so tightly that a single teaspoon of this material would weigh approximately 6 billion tons on Earth. Some of these crushed cores, known as pulsars, rotate at extraordinary speeds. They can spin hundreds of times every second, sweeping beams of electromagnetic radiation through space like a cosmic lighthouse. When astrophysicist Jocelyn Bell Burnell first discovered these pulses in 1967, the timing was so perfectly precise that researchers initially nicknamed the signal LGM-1, considering the possibility they had intercepted an artificial signal from an alien civilization. Even in death, these violently crushed cores retain enough kinetic energy and heat to outshine and outspin almost anything in the living universe. In rare cases, neutron stars form with extraordinarily powerful magnetic fields, becoming magnetars. Their magnetic fields can be up to a quadrillion times stronger than Earth's. To put that in a practical scale, if a magnetar was located exactly halfway between Earth and the Moon, its magnetic field is so intense it would instantly wipe the data off every credit card on our planet. If the dying star is massive enough, it bypasses the neutron star phase entirely and creates the absolute limit of mass, a black hole. The core collapses entirely, creating a gravitational pull so intense that past a boundary called the event horizon, not even light can escape. Astrophysicists now believe there might be one final theoretical frontier, resting directly on the razor's edge between a neutron star and a black hole, the bizarre quark star. If the internal pressure of a neutron star is extreme enough, the neutrons themselves could break apart into a dense state of raw quarks. While unconfirmed, two distinct candidates for this new state of matter were identified by the Chandra X-ray Observatory. Whether they sip fuel for 1 trillion years or violently explode after a few million, every star in the sky is a ticking clock. Eventually, everything is destined to collapse, transform, and join this bizarre cosmic graveyard.